Welcome all of you. In the previous lecture, we have discussed the basic concept of stability, classification of stability, that is steady state stability, dynamic as well as transient. We have also seen the power angle equation and the power angle curve, the swing equation, and what do you call the steady state stability limit. Okay, so all these things we have seen, and in today's lecture we'll be mainly discussing the transient stability limit or the transient stability, which can be explained with the help of equal area criteria, and we will see some of the application of this criteria in calculating or analyzing the transient stability of different systems. Again, the reference here is Modern Power System Analysis by D.P. Kothari. Before proceeding to today's topic, let's refresh the concept of transient stability. Do you remember what is transient stability? As the name indicates, this transient or transient stability means a sudden and large disturbance occurring to a system. Now, do you remember what do you mean by the stability? It is associated with the synchronous speed of the machine or our synchronous machine. Okay, and this was our swing equation. So what do you mean by swing equation? From the name itself, swing means what? Swinging of what? Swinging of rotor. Okay, that can be determined by the angle delta. What was the angle delta? Angle delta is the displacement of the rotor with respect to a synchronously rotating reference frame. Okay, so with the help of swing equation, it is actually the swinging of our rotor angle delta or the load angle delta. How is it related to the electrical power generated? Okay, or how the mechanical power and the electrical powers influence is there in this delta or in the reverse way. Okay, how this delta influence the electrical power and the mechanical power, like that. Okay, so that is governed by this swing equation. Now, in order to find out the transient stability of a system, we require swing equation. Now, equal area criteria is a very important topic, very important topic, which can be asked as an essay question or its application can be asked as an essay question. Anyways, the concept of the equal area criterion should be very clear so that any type of questions in this particular area can be tackled easily. Now, there are some assumptions. EAC here actually equal area criterion. Some assumptions are there before proceeding. Okay. So first of all, again reminding you of the transient stability. Transient stability means if a system is capable of coming back to its initial state after a sudden or large disturbance, then you can say that that particular system is transiently stable. Okay, and we will be analyzing whether a particular system is transiently stable or transiently unstable with the help of this criteria, that is equal area criteria. Okay, so if a particular system satisfies the equal area criteria, you can say that the system is transiently stable. Okay, so in that case we are putting forward some assumptions here, and that is, again, what is delta? Delta is torque angle or the load angle. Okay, and here where our first assumption is the delta may increase to a maximum value, then decrease to a stable value. We'll say that that system is stable. What do you mean by delta? Delta is a deviation or displacement of the rotor with respect to a rotating reference frame, right? So if this delta varies and then it decreases to a stable state, we can say that our system is stable. The second assumption is when the delta is increasing indefinitely. Delta means what? The displacement from the synchronous. Okay, so when the delta is increasing indefinitely means that displacement is going on increasing, or your rotor is running away from your synchronous speed. That is the meaning. Okay, so in that case you can say that your system is unstable. These are the two assumptions putting forward for equal area criteria. Under this case, I can write, for a system to be stable, your delta should not change. isn't it? So you can say that d delta by dt should be equal to 0. Your delta should be constant. Your delta should not vary. Okay, so that is, for a system to be stable, you can say that the change in delta with respect to time should be equal to 0, or there is no displacement with respect to time. And it is unstable when the change in delta with respect to time is increasing, or it is positive or greater than 0. Okay, that is the change in delta. If the change in delta is greater than 0, means what? Delta is continuously increasing. In such case, your system is unstable. These are the two main assumptions that we required for deriving our equal area criteria. I hope these two assumptions are clear to you. The first thing is, a system can be stable when there is no change in delta, or d delta by dt is equal to 0. A system is unstable if the delta continuously increases, or d delta by dt is greater than 0. Now, with the help of a swing equation, what was our swing equation? You remember? H by pi f into d square delta by dt square is equal to Pa, or H by pi f into d square delta by dt square is equal to Pm minus Pe. What is this Pm minus Pe? Pm minus P is nothing but Pa, that is accelerating power or deaccelerating power. What is Pm? Pm is the mechanical power input. What is PE? P is the electrical power output of the generator. When the mechanical power is greater compared to the electrical power, there will be accelerating power. When electrical power is greater compared to the mechanical power, then your power will be deaccelerating. And when your mechanical power is equal to electrical power, we can say that your system is stable. These things we have discussed in the previous lectures, right? Okay. So this was our swing equation, that is h by pi f into d square delta by dt square is equal to Pa, where h is the inertia constant, f is the frequency, delta is the load angle or the torque angle, Pa is the accelerating power, which is equal to Pm minus P. Okay. Now we can reframe it as m into d square delta by dt square is equal to Pa. What is m? M is the moment of inertia, which is equal to h by pi f. We have seen this. Okay. Or from this I can write d square delta by dt square is equal to Pa. This m over this side. So it becomes d square delta by dt square is equal to Pa by m. Clear? Now I am going to multiply both sides with 2 into d delta by dt. So how it would be multiplying these two sides with 2 into d delta by dt? It would become 2 into d delta by dt into d square delta by dt square is equal to 2 into d delta by dt into Pa by m. Okay. Again, I am rearranging this. 2 into d delta by dt into d square delta by dt square is equal to 2. This m over here. So 2 by m into d delta by dt into Pa. Okay. Again, 2 into d delta by dt into d square delta by dt square is equal to 2 by m Pa over this side. Pa into d delta by dt. Now what I am going to do is integrating both sides with respect to d delta. So what it would be? 2 times integral d square delta by dt square into d delta is equal to 2 by m Pa d delta. Okay. Now what it would be? So here into dt would get cancelled, right? So here there was one dt, here also in the denominator there was one dt. Okay, so that got cancelled over here and you got the final thing like this. So it is now with respect to d delta that we are integrating. So it would be, what is the integral of this d delta by dt the whole square? That is the integral of d square delta by dt square. Okay, now it would be equal to 2 by m. Here what it would be? Integral Pa d delta. Okay, and what can be the value of delta? Value, we can apply some limit, right? And the value of delta can be from an initial value to a final value, that is d0 to delta 0 to delta. Okay, so I'm rearranging it as d delta by dt is equal to root of it was d delta by dt, the whole square is equal to this much. So I can write d delta by dt is equal to root of 2 by m. Again the same thing, delta 0 to delta PA into d delta. Now for the system to be stable, what should be the condition? D delta by dt should be equal to 0. That means this d delta by dt should be equal to 0, or root of 2 by m integral delta 0 to delta into PA into d delta should be equal to 0. But you can say that 2 by m, can 2 by m is equal to 0? No. Then you can say integral delta 0 to delta PA d delta is equal to 0. Now, what is this PA? PA means PM minus PA. That thing is equal to 0. So from that, you can say that, what do you mean by integral of something? Integral of something means what? It is nothing but area, isn't it? So the area of the accelerating power is equal to 0. That is the meaning. Or I can say that area of mechanical power is equal to area of electrical power. Okay. So you can state that the condition for stability can be now stated as the system is stable if the area under PA delta curve reduces to 0. In other words, an accelerating area under PA delta curve must be equal to the deaccelerating area under the PA delta curve, and hence the name equal area criteria. So what did we derive actually? We have derived with a condition for the system to be stable, d delta by dt should be equal to 0. For d delta by dt to be equal to 0, this is the condition you obtained. What does this condition indicate? Integral of something is equal to 0. That means integral of something means some area. Okay, what area? The area of the graph between P and delta. Do you remember any graph between P and delta? What is this graph? This axis as P and this axis of delta. What is this curve? This curve is actually your power angle curve, right? Okay, power angle curve. This is electrical power P. This is our power angle curve. In this curve, what all areas should be equal to, what all areas is equal to 0? Accelerating area should be equal to 0. So in this curve, some areas are there. Let this be one area and let this be another area. And what is this area? This area corresponds to PM. If this area corresponds to PM and if this area corresponds to PE, and if these two areas are equal, you can say that your system is stable. Okay, what do you mean by PM minus PE is equal to 0? Simply means your PM area is equal to P area PE over the delta curve, isn't it? So this indicates for a system to be stable, your accelerating power should be equal to the deaccelerating power, or you can say the total net power is equal to 0. Okay, if this is attained, you can say that your system is transiently stable. Now this idea will be much more clear by looking into the applications. Okay, so we'll see which are the two areas and everything like that. So we can say that the condition for stability or by equal area criteria is that area under PA delta curve. What is the PA delta curve? Remember, PA delta curve is our power angle curve. So area under the PA delta curve should reduce to 0. Or we can say that the accelerating area of the PA delta curve must be equal to the deaccelerating area of the PA delta curve, and hence we call this criterion by the name equal area criteria. Am I clear? This equal area criteria derivation is very important. Now this concept of equal area criteria will be much more clear to you if we discuss the applications. Now we will see one application where we will say sudden change in mechanical input. Now we will see to it what actually it is. Okay. So here consider a system is shown here. This is our generator, this is the transmission line, and all this is the receiving end voltage. So if this is a sending end voltage E and the receiving end voltage is V and the transmission line reactance is XD dash and XE, you can say that what is this equation? P is equal to P max sine delta. This is our power angle equation, right? P is equal to P max sine delta. And what is this P max? P max is nothing but sending in voltage into receiving in voltage divided by total reactance. Okay. Now let's draw the curve. Here, this is the power angle curve, and this is the curve that we have drawn here. Now just concentrate on this curve actually. Okay, curve actually. Now under steady state operating condition, what is the case? Steady state operating condition, we have assumed it like, right? For steady state operating condition, your mechanical power should be equal to electrical power. Let the initial mechanical power is Pm0, which is equal to your electrical power Pe0 if it is a steady state condition. And what is Pe0? It would be equal to Pmax sine delta, or rather I can say P max sine delta 0, where delta 0 is the initial load angle. Okay, so I can say that this is a power angle curve that I have drawn, and here I have written mechanical power. What is the mechanical power? Mechanical power is nothing but our steam input, right? It depends upon the steam input. If the steam input is constant, your speed of your turbine is also constant, or I can say that the mechanical power is also constant. So this line indicates this line. Okay, this line indicates the mechanical power, initial mechanical power. It's a constant value, and we can say under steady state condition, this mechanical power is equal to the electrical power. Okay, so let's see this point A. Okay, you can see this point A, right? This point A. So this was your power angle curve, and this curve actually represents the electrical power, right? Electrical power. So the electrical power here, this is the electrical power under the initial condition, because at this electrical power you can say the mechanical power and electrical power are same. That means this common point. This is the electrical power initially. Or I can say the delta corresponding to that is delta 0. Okay, delta 0 was our initial load angle, and corresponding to that delta 0, this is the corresponding electrical power generated, which is equal to the mechanical power because it is under the stable condition. Under the stable condition means your machine is rotating at a speed is equal to synchronous speed. So I have marked it as omega s, the speed. I hope this much is clear to you. Okay, this is a normal operating condition of a machine. You ignore about the other cases. You just concentrate about this curve and this line now. Okay. Now, what is the next case? This was a normal operating condition. Suddenly a disturbance occurred to the system. And what was the disturbance? Let the mechanical input to the rotor is suddenly increased from PM0 to PM1. That means the machine was working for a particular steam input. Suddenly the steam input has increased. So what will happen to your machine? The mechanical power also increases from PM0 to PM1. Okay, so initially this was your mechanical power. This line was your mechanical power. But suddenly now this mechanical power increased from PM0 to what? PM1. So now this line is your new mechanical power. Okay, this line is your new mechanical power. Now we can say that now what was your electrical power? This is now your electrical power. But what is your mechanical power? This much is your mechanical power. I'll make it much more clear to you. See, this much is your electrical power now. But this much is your new mechanical power. Now can you say that your electrical power and mechanical power are same? No, your electrical power and mechanical power are different. Which is higher? Your mechanical power is higher, isn't it? Mechanical power is higher compared to the electrical power. So what will happen? What will be the net power? Net power is equal to Pm minus P. Okay, so here Pm is greater compared to your electrical power. So I can say that your net power is positive or accelerating. Or rather, I can say that the mechanical power is higher compared to the electrical power. So what will happen to your rotor? Rotor will start accelerating. Okay, so your rotor will now accelerate. Once your rotor increases its speed, what will happen to your rotor angle? Rotor angle also increases, isn't it, from delta 0. So initially this was the case, stable case. But now what happens? When the rotor accelerates, your rotor angle also accelerates, and now it moves like this. It is increasing, right? Okay. Now, and it is increased and a point has reached this. And at this point, when a rotor angle increases, what happens to your electrical power? You know that electrical power is equal to a function of sine rotor angle. So when your rotor angle increases, your electrical power also increases, right? So when your when your rotor angle increases from delta 0 in this way, you can say that your electrical power is also increasing correspondingly like this. Am I clear? And once the rotor angle reaches delta 1, you can say that your electrical power is this much, isn't it? This much is your electrical power. And at this point, you can say that your new electrical power is equal to the mechanical power. Am I clear? New electrical power is now equal to the mechanical power, which means what? Whenever your electrical power becomes equal to the mechanical power, the machine will be under stable condition, isn't it? At delta 1, you can say that mechanical power is equal to the electrical power, or your accelerating power is equal to 0, or a stable state is reached. Okay, so the angle is supposed to be stable here, but what happens? The rotor angle continues to increase. Why? Because the motor was accelerating or the rotor was accelerating, right? And at this particular point, can this machine suddenly stop? No, the rotor angle continued to increase. Why? Because of the inertia of the machine. Actually, the machine wants to stop here, but it will not stop because of the inertia of the machine. So your rotor angle will continue to increase in this direction. Make clear? So your rotor angle will be continues to increase in this direction. When the rotor angle increases in this direction, what will happen to your electrical power? Electrical power also again increases like this, isn't it? Excuse me, sorry. So your rotor power also increases, like, see, when your rotor angle increases, the electrical power also increases like this. Okay, now assume another point, it has reached at another point. Okay, delta 2. Assume another point delta 2 here. At this point, how is your electrical power? How is your electrical power? I can say, at this point, I can say this much is your electrical power. But what is the value of your mechanical power? Mechanical power is constant, right? This much is your mechanical power. So this much was your electrical power and this much is your mechanical power. So what happens? Your mechanical power is less compared to your electrical power. What will happen to the net power? Net power is negative, right? When the net power is negative, what will happen to your rotor? Rotor will decelerate or deaccelerate, isn't it? When the rotor deaccelerates, what happens? Load angle also decreases. So load angle reached this point and now the load angle continues to decrease in this direction. When your load angle decreases in this direction, what will happen to your electrical power? Electrical power also decreases in this direction. Am I clear? In this direction, but again it reached this point. At this point, what happens? Your electrical power and mechanical power are same, but your rotor continues to decelerate. Why? Because of the inertia. So what happens? The load angle continues to decreases from delta 1 towards this point. Correspondingly, electrical power also continues to decrease like this. Okay. Again, once it reaches here, what will happen? This is your electrical power and this was your mechanical power. Your mechanical power is high compared to your electrical power. What will happen now? What will happen now? The machine will accelerate. That means in this direction. When when the rotor angle increases in this direction, electrical power also increases in this direction, isn't it? So in this way, your machine's operating point will change from A to C. Again it reaches A, C. Finally, after this swinging, that is, the machine will swing between the points A and C, and finally it will reaches a steady point B where your electrical power is equal to mechanical power. Am I clear? Is this concept clear to you? So, now we are going to apply our equal area criteria here. Okay, from the figure, what is the first area? We are considering about the accelerating area and the deaccelerating area. Accelerating area means mechanical power higher compared to the electrical power. Now we will find out what is that area. Can you see? Mechanical power. Okay, this area, mechanical power, between mechanical power and electrical power. This curve is actually corresponding to electrical power, whereas the straight line corresponds to mechanical power. So what is the area? Area Pm minus Pe, between which all limits? Delta 0 to delta 1. So between delta 0 to delta 1, what is the area? Pm minus Pe. This much, right? This is the first area. This is the accelerating area. Okay. Now from delta 1 to delta 2, the machine, from delta 1 to delta 2, which is higher? Electrical power is higher compared to the mechanical power, isn't it? So from delta 1 to delta 2, which is the area? Pe minus Pm. Okay, because electrical power is higher compared to mechanical power. So this is your second area or deaccelerating area. But from delta 0 to delta 1, your mechanical power was higher compared to your electrical power. So this is the accelerating area. So you got two areas. A1 is the accelerating area and A2 is a deaccelerating area. Now, according to equal area criteria, for this system to be transiently stable, the two areas, that is accelerating area and the deaccelerating area, should be equal. Now, let's see the analysis. From this figure here, this is what we have discussed. So, A1 area, first area is from delta 0 to delta 1, Pm1 minus P T delta. And the second area is from delta 1 to delta 2 where electrical power was greater, right? So Pe minus Pm1 into T delta. For the system to be stable, what should be the condition? For the system to be stable, the two areas should be equal. Okay, or at least your A2 should be greater than A1. This is a condition. Okay, A1 is equal to A2. Now let's see this. Now in this particular case, assuming that your A1 is equal to A2, no issue. Okay, so the main case is that your accelerating area should be less than your deaccelerating area. Whenever your accelerating area becomes greater than the deaccelerating area, the machine will loses its synchronism. Okay, so here now we are assuming another case. Now Pm is further increased. Okay, this is one case, another case, right? As a Pm is increased, so this is the maximum value of delta 2. Here beyond which I cannot have any delta, isn't it? This is delta 1, this is delta 2. Now this is a condition. Under this condition, D2 is delta 2 is a maximum value. This is a maximum value. Now if further I cannot increase the delta so as to make these two areas equal. Okay, so that's the case here. Now if you any further increase in the P, if I am increase the mechanical power like this much, this is your, sorry, let This is your new mechanical power. Okay, so that means your area would be somewhat this much, right? This much would have been your first area. Okay, and your second area would be only this much. So from it here itself you can see that this area becomes greater than this area. So your system will become unstable. Okay, so that means this will be your delta 2. Right? Okay, so beyond which I cannot increase. Okay, so for a particular mechanical power input, I can increase the value of delta. This is a maximum value with which you can say that your accelerating area is less than your deaccelerating area. That means your accelerating area should be at least less than or equal to your deaccelerating area A2 for the system to be transiently stable. We cannot blindly say that always A1 should be equal to A2. That is the maximum limiting condition. Or at least your accelerating area should be always less than or equal to your deaccelerating area. This is the condition. So with this condition, by keeping this criterion, you can say that a system can be transiently stable. So in this particular case, now coming back to this particular case, okay, coming back to this particular case, here you can say that for this case, this is a maximum value of delta because there is no value of delta available here. Okay, there is no value of delta available here. So this is the maximum possible value of angle delta. So you can say that your delta 2 or the maximum value of delta maximum is equal to what is this much is pi. Okay, so pi minus delta 1. It is same as pi minus delta 1, right? So what is this much angle? This much angle will be equal to the entire thing pi minus this. This is simply but delta 1. Okay, so pi minus delta 1. So what is this delta 1 actually? What is this delta 1? What is this delta 1? In that, that is nothing but PM1, right? PM1 is equal to, what do you call PM1 is equal to Pmax sine delta 1, isn't it? That is the equation. PM1 is equal to Pmax sine delta 1. Pmax sine delta 1. From this I can write delta 1 is equal to sine inverse PM1 by Pmax. Okay, so in this way you can find out the maximum value of delta. So with the main application of this equal criteria is that in order to find out two areas, that is accelerating and deaccelerating area, and whenever you see that your accelerating area is less than or equal to your deaccelerating area, your system is transiently stable. Okay, your system is transiently stable. So that was the case when you increase the mechanical power. Now we will see at another case. Here again we are consider the sending end voltage and everything are same. Now in this case again the same assumption is there. Initial condition mechanical power is equal to Pm and initial electrical power let it be Pe0. The angle corresponding to that is delta 0. So this is our power angle curve and this is our mechanical power. So you can say that initially your machine is operating at this operating point A. Okay, this is your operating point A and corresponding to that your load angle or torque angle is delta 0. So harmlessly your machine was operating under the stable condition, or otherwise I can say that at synchronous speed. Okay, so suddenly what happens is that a three-phase fault occurs. Okay, it was at this point a three-phase fault occurs, and what happened when a fault occur like this, electrical power from the machine here, the electrical power is equal to 0. Oh, so when electrical power reaches 0, what happens? This was the actual electrical power. Now when the electrical power reaches 0 means from this point your electrical power decreased and reaches 0. this point. Okay, so this was first operating condition. Suddenly a fault occur, your electrical power dropped from PE to 0. That means this operating region. So now what happens? Now your electrical power is 0, whereas this much is your mechanical power. What happens? Mechanical power is greater compared to your electrical power. When the mechanical power is greater, what happens? Acceleration occur. Your motor or the rotor starts accelerating. When the rotor starts accelerating, what happens to the rotor angle? Rotor angle also increases like this. Okay, rotor angle also increases, and at this particular event here, when the rotor angle increases, you cannot say that your electrical power is increasing. Why? Because due to the fault your electrical power is now 0. Until that fault is clear, there will not be any electrical power. Okay, now let's at this particular point C, that is at the particular point this, or at the corresponding load angle, your fault is cleared. So if from this point, or at this point, if your fault is cleared, what would be the corresponding electrical power? The corresponding electrical power will be this, right? So that is a corresponding electrical power corresponding to this angle. Okay. So now this much is your electrical power, whereas this was your mechanical power. So what is the condition now? At this point, your electrical power is greater compared to your mechanical power. So machine will start decelerating. But what will happen due to the inertia? The load angle will continue to increase from delta C. From delta C, the load angle will continue to increase due to the inertia. When the load angle increases in this way, what happens to your electrical power? Electrical power also increases in the similar fashion. Okay, now let at this point, or the corresponding here, from this point what happens? Let your machine starts decelerating. Okay, from the machine starts decelerating means now what happens? Now what happens when the machine decelerates? So let your load angle decreases like this. Okay, now in this way it deaccelerates, and finally it will reaches again at the same operating region A, where mechanical power Pm is equal to the electrical power Pe. Okay, am I clear? So finally your machine will be settling down at this point A, where electrical power is equal to mechanical power. The entire thing happens when the fault is cleared at this point, and this delta C is called clearing angle. What clearing? Fault clearing. Okay, clearing angle, and the time corresponding to this angle is called clearing time, T. Okay, so you can say that at this particular point your fault is cleared by opening the circuit breaker, or by some other means your fault is cleared, and this angle at which the fault is cleared is called clearing angle. Now how can you say that your system is stable? So for your system to be stable, two areas should be equal. What are the two areas? Accelerating area, that is Pm minus Pe, and deaccelerating area, that is Pe minus Pm, should be equal. Or at least accelerating area should be less than your deaccelerating area. Now let's see what is the accelerating area. Accelerating area is from this point to this point, isn't it? Because from this point to this point you have mechanical power greater compared to your electrical power. So this much is the first area, A1, or accelerating area. Now, second case is the deaccelerating area, PE minus PM. That is from delta C to delta 1. Your machine is deaccelerating, or that is PE. This is a PE and this is a PM. So, area between PE and PM. Okay, these two areas, if these two areas are equal, you can, or at least first area is less than your second area, you can say that your system is transiently stable. Now in this context, what can you say? Can you just judge what will happen? Fault is not cleared at this point. Instead your fault is cleared at some point like this. So what will happen? What will happen to your first area? Now this much will be your first area, isn't it? This much will be your first area and only this much will be your second area, right? So you can say that if the fault is cleared only at this particular angle, you can say that your accelerating area is greater than deaccelerating area. So what happens when accelerating area becomes greater than deaccelerating area? The system will not be stable. The system will lose its synchronism. So in this case, I can say that there is a particular angle beyond which if you delay the fault clearing, these two areas cannot be equal, isn't it? So we are going to find out what is that particular angle or what is that critical angle with which within which the fault has to be cleared unless otherwise what will happen? Your machine will move out of synchronism or the machine will loses its synchronism. Now let's see what that concept is. The very same system, okay, the very same system, I think in the previous system we have cleared the fault at this point, isn't it? Okay, now just leave it. If we have not cleared the fault at that particular point and we have cleared a fault at another point, okay, that a particular point at which your two areas are equal. So in the first case you can say that the first area was less. Okay, this was the first case. Okay, if I am increasing this area, A2 also can be increased in order to compensate with A1. Okay, so as to make these two areas equal. Now in this case, if I have delayed the fault clearing and this is a new point at which I have cleared the fault. Okay, now for the system to be stable, both areas should be equal. Now let's see how I can say this both areas should be equal. What is this first area? First area is integral delta 0 to delta CR. We will call this angle as critical clearing angle. So integral delta 0 to delta CR, PM minus PE should be equal to the second area. What is the second area? Integral delta CR to delta 1 PE minus PM. Okay, now let's see. Now let's see what is this delta 0. Okay, and what is this delta 1. Okay, that all things we have seen, right? Your delta 1 or your maximum value of delta. Can you increase your delta further here? No, further if you are increasing there is no curve for like that, isn't it? You cannot increase it. Now what will happen now? Now let's see what is this delta max. Delta max is same as pi minus this much angle. That much angle means same as this much angle. Okay, so pi minus this much. What is this much? Delta 0. Okay, so what is delta 0? We have seen sine inverse Pm by P max. Now what is P equation? P max sine delta. Now at delta 0 you can say that PE is equal to PM. Or I can write instead of PE, I can write as PM. PM is equal to P max sine delta 0. Okay. Now, or I can say that delta max is equal to pi minus sine inverse Pm by P max. Now we are finding out the two areas. What was the first area? Delta 0 to delta CR, Pm minus PE. But here PE was equal to 0. I can write delta 0 to delta CR, Pm d delta. That is equal to Pm delta within the limit. So this is the first area. Second area is from delta CR to delta max, PE minus Pm. Okay, or delta 0 to delta CR to the max, P max sine delta minus, so instead of PE I can write it as what? P max sine delta. Instead of PM we wrote it as PM itself. Okay, so after expanding this was the equation we got. Now these are the two areas we got. Now for the system to be stable, what is the condition? A1 should be equal to A2. Okay, so delta CR, from this I can write it as, I can equate these two. these two areas can be equated, and from that equation we have written what is delta CR is equal to. We got like this, cos inverse pi minus something like this. Okay. Now this delta is called critical clearing angle or delta CR. Now we know that as per the swing equation, d square h by pi f into d square delta by dt square is equal to Pm minus Pe. But here Pe is equal to 0, so I can write it as h by pi f like Pm. Okay. From this we return d square by dt square is equal to pi f by h into Pm. Now on both sides if I am integrating, I will be getting it as delta. If I am integrating once, I will get it as d delta by dt is equal to something. Similarly, if I am integrating 2 times, I can write delta is equal to pi f by 2h Pm t square plus delta 0. Delta, where delta 0 is an initial value or constant. Okay. Now, if this delta is equal to critical clearing angle delta CR, I can write this T or time is equal to critical clearing time. So, from this equation, I can write critical clearing time is equal to root of 2h into this thing. What is h? Inertia constant. What is Pm? Mechanical power. Now, what does this angle actually indicates? What do you mean by this critical clearing angle? So this angle is called critical clearing angle. Why is it called critical clearing angle, or what is critical clearing angle? So critical clearing angle can be defined as that angle beyond which what happens? So fault has to be cleared maximum at this angle, or fault has to be cleared uh, below this angle, because beyond the critical clearing angle, what happens if the fault is cleared? Your area A1 and area A2 will not be equal, and your area A1 will be greater than A2, and your system will move out of synchronism or will be transiently unstable. So that maximum value of angle beyond which your system will loses its synchronism is called critical clearing angle. That means if any fault occur to a system, that fault has to be cleared within this critical clearing angle. Okay, if your critical clearing angle is 90 degree, your fault has to be cleared before your load angle reaches 90 degree. Am I clear? What will happen when your load angle will become greater than 90 degree? When it becomes greater than 90 degree, the these two areas will not be equal, and your accelerating area will be greater than your deaccelerating area, and the system will move out of synchronism, or we can say the system will be transiently unstable. Okay, now the time corresponding to that angle is called critical clearing time, or I can say that fault has to be cleared within that critical clearing time. If the fault clearing goes beyond the critical clearing time, machine will lose synchronism, and which it will move out of stability. We will call that system as transiently unstable. So this is one another application of equilibrium criteria, because with the help of equilibrium criteria here we have calculated the critical clearing angle of a system or the critical clearing time of a system, which is very crucial in determining in the fault calculations and everything like that. So whenever a fault occurs, the critical clearing angle or critical clearing time plays a crucial role in the stability of power system. So this can be asked as a short answer question. What is critical clearing angle and what is its significance on power system stability? What is critical clearing angle? So angle below which this fault has to be cleared. So what is its significance in stability? Because if the fault clearing is delayed and if the load angle is greater than the critical clearing angle, the accelerating area becomes greater than the deaccelerating area, and it will violate equilibrium criteria, and system will be transiently unstable. So that is the significance of critical clearing angle on power system stability. Okay, so here in this context I can say that the most important derivation here it is equilibrium criteria, and the equilibrium criteria is actually for analyzing the transient stability of a system. Remember, transient stability of a system. not steady state stability. What is transient stability? Transient stability means whenever a sudden or large disturbance occurs to a system, whether the system is capable of returning back to its initial states or not. That is actually transient stability. And that transient stability of a system can be analyzed with the help of the criterion called equal-area criteria. And what is equal-area criteria? As long as the accelerating and deaccelerating area of a system are equal, maximum, that is equal, your system will be transiently stable. Otherwise, whenever your accelerating area becomes greater than deaccelerating area, the system will be unstable. So by keeping that in mind, we have seen the fault clearing and what will happen when mechanical power input is varied, what is the effect of mechanical power input variation onto the stability also can be explained with the help of equal-area criteria. And so this is the application. This can be asked as an essay question, equal-area criteria, and critical clearing angle or the critical clearing time can be asked as a short answer question. So far we have discussed about the different types of stability, transient stability, and method of analyzing transient stability is nothing but equal-area criteria, critical clearing angle, critical clearing time, and that equation is also very important, how to calculate that critical clearing angle and critical clearing time. So hope this much is clear to you. If you have any confusions in any area, please contact me in person. I can help you in working out with that case. So please study well this equal-area criteria definition and the basic concept of equal-area criterion and critical clearing angle and stability. Thank you.